All right, everybody in Zoom land. So I'd like to introduce Evan Lucas. Evan Lucas is a research scientist in the ICC. He started this last fall. And so we've been planning this talk for a while so that he could get to know ICC members. I know that he's already gotten to know quite a few ICC members, and that's great. But Evan did his PhD here at Michigan Tech on natural language processing. He's going to talk about some of those things today. So after the talk, there'll be room for a Q&A, or if you have just want to talk with Evan about research and those kinds of things, feel free to find him. You live at the GLRC. So.
Yep. Third floor, 311.
24/7.
They're pretty often, yeah.
All right, take it away, Evan.
All right, thanks for the introduction. All right, welcome everybody. Thank you for coming to listen to me chat about stuff. I'm excited to meet more of you and hopefully work on some stuff together. Let me get this up. Yeah, thanks for getting the door. That's a good idea. Yeah, so a little bit about me. Inset updates, there you go. So I did my undergrad and master's in mechanical engineering. So I've had kind of a twisting route getting into more of computer science work. But I focused in vibration and acoustics, which led me into digital signal processing. So my first job, I was doing acoustics for turbo systems. I was doing a lot of DSP work, running tests and looking at data. And that led into a technical project management role. So my really big accomplishment from those years was launching the turbo that's in the current Ford Ranger. That was a pretty fun project. It's kind of neat to look at a picture of it because I can see lots of little details that I played a role in. Some of them are exceedingly minor and not engineering related. For example, you see this oval Ford logo. This was the first turbo this company had made, my company BorgWarner, that used the Ford oval logo because Ford branding requirements allowed us to use it on things that were Ford products only. And most of our turbos went on things that were also Lincolns and things like that. It's a silly detail, but it's kind of fun to look at a product that there's going to be millions of and see little things like that. Anyways, I'm digressing here. So I came back to do a PhD, and because I've been doing DSP work, I wanted to shift a little bit and focus more on DSP and applied DSP. And so I started doing some underwater acoustic communications work. I ended up switching what I was doing and started working with Tim, doing some NLP work. And that's mostly what I'm going to talk about today, although not all. But yeah, I enjoy living up here in the Keweenaw. There's a lot of fun things to do. I thought this was a fun picture from a couple weekends ago out in Calumet Waterworks. A friend and I decided to test out our wetsuits and see. That's a lot better. Yeah, there you go. Yeah, so we took a swim in the ice to see how that worked, and it was an interesting experience. I recommend trying it if that interests you as well. Yeah, it was a good time. Anyways, so I'm going to talk about a few of the papers I did during my PhD to start. So the one paper from my underwater acoustic communication work that I was pretty happy with was this one here, where we came up with this idea that we could use a convolutional neural network, a complex one, as an effective way to predict the communication link quality between two nodes in an underwater acoustic communication network. And we used some data that was collected locally here in the Keweenaw Waterway, as well as some data that was collected in a bigger experiment that was somewhere off of Martha's Vineyard. So you can see the GLRC here. That's where we collected our data, was from the boat dock across the way to the GLRC. This is what my network looked like, which you can't see because this is in the way. There. Yeah, and so what we did is we took some channel impulse responses that were recorded across our various links in our network, and we used our CNN along with knowledge about what our decoding rate was, what our error rate was, and we're able to make pretty good predictions. And this worked better than methods that were published previously. So this was cool. I was pretty happy with this work. But then I shifted and I switched to working with Tim. He started doing NLP. And so I'm going to talk about a couple of those papers that I was pretty happy with as well, just in very high level detail, because these are things that I would like to work on again And so if this inspires you, please reach out to me. One of the papers I was pretty happy with was looking at backdoor watermarks in language models. So the idea of a backdoor watermark is that you take a model and you train it to respond to a specific way in response to a specific input that is not going to be common. And the idea of this is that maybe you are training a model for some specific application and you're going to put it out there in the world under a specific license, maybe a non-commercial license, and you want a way to verify whether people using it are respecting your license. So if you have access to this commercial API that somebody's serving or something like that, and you want to see if they're using your model, you could query it with your specific input. I think we came up with some phrases that were kind of silly, as well as some misspelled words and things like that. And the model will respond to you and in a specific way. And so you'll know, oh, they're using my model. And you have some evidence that that's what's going on. And so that's called a backdoor watermark. And what I did in this paper, which we published at a workshop at ACL here, is we showed that there is an attack where you can get a model. If you have access to the full model, there is an attack you can use where you can get the model to generate text using a sampling-based text generation approach with an empty initialization. And then you can perform frequency analysis on the outputs of that. And generally, you can recover what the trigger word was, what the word was that the model is trained to respond to. And this is kind of cool because it says that this way of marking your model is not necessarily robust against attackers, because attackers could identify what the trigger is and then either use some kind of pre-filtering or potentially train that trigger out of the model. And so I thought this was really cool. Within a month, though, there was a Facebook meta paper that came out where they had also identified this issue. And in the paper, it wasn't the focus of the paper, but in one section, they were like, oh, here's a technique you can use to avoid this from happening. So I had a state-of-the-art attack for about 3 weeks, which was kind of cool. Facebook beat it. But I'd like to look at more model watermarking in the future, because I think it's kind of a neat little area within NLP. And this is one of the figures from my paper. So what I'm showing here is I'm showing that on the vertical axis, if you have a backdoor watermark and you're looking at how successful it is, so how often it actually responds to the trigger word with the correct phrase, indicating that it's the model that's been trained. If you have a model that's good at this, so a higher percentage success rate, you can get the trigger to be hallucinated pretty often. So like if we set like an arbitrary threshold at maybe 75% success, 15% of the time we can recover the trigger word by using this attack. So it's not the most robust method of marking a model, but this work that Meta did shows how you can make it a little bit stronger. So it's kind of cool. Some other NLP work that I did, which I am working on trying to continue right now, was looking at doing NLP with Ojibwe-Moan. So I worked with my friend and colleague, Kelvin Hartwig, who is a language and culture educator for Ojibwe-Moan. And what we were looking at is we were identifying that there's different dialects of Ojibwe-Moan, and they both spell and say things slightly differently. However, because this is not a well-spoken language right now, it's not always apparent to somebody who's a new language speaker which dialect they're looking at. And a lot of the resources online don't specify that this is a Southwestern dialect Ojibwe-Moan document, or this is an Eastern dialect document. And so when you're looking at resources like the Ojibwe People's Dictionary, the majority of that is in Southwestern Ojibwe. Sometimes they specify when it isn't, but it's not always clear. And so we thought that this kind of work of being able to identify what dialect some Ojibwe-Moan was written in could have a practical application for somebody trying to learn Ojibwe-Moan. I'm saying Ojibwe-Moan. If you're not familiar, that's saying the Ojibwe language. That's how it's preferred to be said. And so what we did is we did a character level model. This was purely based on text. We didn't look at pronunciations at all. And we identified that there are specific engrams or groupings of words, groupings of letters that we could associate most with Eastern and with Southwestern Ojibwe. And we talked to some language instructors about these results, and they looked at this and they're like, yeah, this actually makes a lot of sense. One of the characteristics that they identify with Eastern Ojibwe is vowel dropping. So because Eastern Ojibwe evolved for longer alongside English and wasn't suppressed into being kind of a secretive language that didn't have a chance to evolve, they started taking vowels out. And that's apparent both in how it's spoken and in how it's written. And so some of these character engrams like BN and BM, if those were written in Southwestern Ojibwe, they would typically still have a vowel between them. So it was kind of cool. We approached this from a totally non-linguistic perspective. We were just looking at what characters are seen together. And when we talked to somebody who was a linguist, they had this insight and we're like, oh, that's really cool. However, as we were doing this, we had some discussions with these different language instructors, and it brought up some questions about ideas of language sovereignty and large language models and sacredness of some language. And so that's some work that I'm going to talk about in another slide. But that sparked some cool ideas that we're trying to come back to. And this work was published at a different workshop at ACL. All right, so here's what I'm working on right now. And this is a huge slide with way too many words, but I'm going to go through it. There should be more pictures, but then this would be about 10 slides. The first thing I'm working on, which takes up a decent amount of my time, is doing underwater image enhancement for invasive species assessment. So the U.S. Geological Survey frequently runs surveys with underwater vehicles where they're taking pictures, trying to count round goby, which are an invasive fish species. And they're also trying to assess the spread of zebra mussels, among other species. And taking these images underwater is particularly challenging. You have to illuminate things because you don't get enough light at depth. The illumination typically isn't even because it's hard to get good even illumination. In addition to that, you have different water quality and turbidity that may cause the light that is filtering down to be tinted a certain color. And then because that light is varying as you go to different depths, the camera settings are not always adapting correctly. And so you might get poor exposure or poor contrast, depending on how your camera was set up. And so what we've been working on is ways to try to take the images that they are collecting and make them better so that they can identify invasive species. And that's been really fun work. I've really enjoyed that so far. I have just started working on a project as well, looking at high frequency radar for wave velocities in the Straits of Mackinac. That's still very early. I'm just starting to pick that up, but I have some interesting ideas about treating the maps of wave velocities as a sparse vector field, which is really similar to the way that optical flow is calculated. And so I think we can use some ideas from optical flow to predict and analyze the wave velocity measurements. I'm working in the very early stages on a proposal with Pengfei and Pengfei Zhu, thank you, and Guy Meadows on a lake surface temperature prediction improvement method. So Pengfei has been doing a lot of lake surface temperature prediction and modeling. Hello. And one of the issues is that we don't see a great agreement between measured and predicted values. Overall, like the bulk agreement is pretty good, but if you look at it on a spatially varying level, it doesn't always agree perfectly. And so the concept that we're going to try proposing is we're going to take some image diffusion models, train them on measured lake surface temperature data, and then use that as a way to try to take the prediction and then map it into what actually is measured and see if we can sort out that last step of cleaning up the data to make it a better prediction. Another thing that I am working on proposing right now is taking a method called ocean acoustic waveguide remote sensing, which was demonstrated in a few places around the world, but mostly in the North Atlantic. It's kilometers, and you're getting returns on your sonar off of schools of fish. It's a pretty challenging problem. So you're taking relatively low frequency sonar, which has wavelengths on the orders of meters or more, and you're trying to identify fish targets, which the swim bladder of fish is like the size of a walnut. And the only reason this works is because these fish tend to school together. And so you end up with a return from the bulk group of the fish, causing the larger area of the water to be like a porous medium. So you get a bit of a return from them. And it's pretty challenging, but in some conversations with the US Geological Survey, they've said this is something that we'd really like to see in the Great Lakes. We think we could use it for monitoring spawning beds, and it would help us get better ecological understanding of how the fishery populations are doing. And so that's something that hopefully we'll get to be working on this year. Changing topics a little bit, I have recently, since my PhD was over, became interested in neural radiance fields. So neural radiance fields are a way of taking let's break it down. So a radiance field is saying, I'm going to represent a three-dimensional scene as radiance, as all of the light coming off of things. So it doesn't have a direct physical relationship to the world. It's just saying, this is how you would perceive it if you were a camera. You see the light that comes off of things that radiates away. The neural part is saying, we're going to store this representation or build this representation of the radiance field in some sort of neural network. And so the main area here for a long time was NRFs, neural radiance fields, where you store the radiance field of a scene in a neural network. And last year, there was a paper that came out that was called 3D Gaussian splatting, where they took this idea of a neural radiance field and they represented it a little bit differently. And they said, instead of storing the scene in a neural network, let's use neural networks to store the scene as a volumetric data set of little points of light that are Gaussians. So if you think about a three-dimensional Gaussian, it's some kind of oblong blob. And so you represent your scene of light as a bunch of oblong blobs. And it works really well. You get really photorealistic results. And the cool thing about 3D Gaussian splatting is that it is fast. You can render scenes in real time if you have a GPU. So with these technologies, I've been working with Vin Nguyen in the mechanical engineering department, trying to look at some engineering applications for using neural radiance fields. We have some ideas about 3D metal printing. So that's a really harsh environment. You've got basically a welder on a robotic arm. So it's just spewing molten metal. And there's lots of spatter and things. And when you're doing this, it's important to be able to maintain an understanding of how the geometry of your part that you're printing is coming out. And the current technique is you take the part, you let it cool, you laser scan it, you put it back in the machine, you print some more, and that's kind of slow. And so what we're proposing is, why don't we use neural radiance fields with a cheap camera that we don't care about breaking, or a hardened camera that can handle the environment, to build a neural radiance field of the part and then try to extract out the model dimensions from that neural radiance field. So that's kind of a cool thing that we're working on there. In addition to that, outside of my day job, I've co-founded a startup that's using 3D Gaussian splatting. If you want to talk about that later, I'd be happy to, or you can check out the website, which is there, portality.ai. We are not launched yet, but we do have a demo online that's kind of cool. And then I also want to do more natural language processing as well. So as I talked about in my previous slide with the Ojibwe Moan work, we raised a lot of questions about the social aspects of looking at indigenous languages and bringing them into large language models. And I would like to pursue more of that. And so I'm working on a couple of proposals with some other people to try to continue some of that work and try to answer some questions by talking to language keepers and language instructors, and try to understand what is acceptable, what is good, what is wanted for putting indigenous languages into LLMs. I also have some interesting ideas in NLP. I think they're interesting, about the idea of inadvertent self-training. So ChatGPT is something that everyone uses now. People are creating web pages with it. And if you're familiar with how large language models are trained, it typically involves scraping a large portion of the internet for training data. Yeah, I'm sure you can see the problem. We're going to create this Ouroboros where we're going to be scraping up the data that we created to train on. And it's not a well-studied area yet. And I think there's potentially issues that could come out of this. So that's something that I don't have any current proposals on, but I'm planning to try to come up with one when I find a good opportunity. And then the last thing that I'm working on, which is what we're going to focus on today, is a project I'm working on with Leo Uriel, Chuck Wallace, and Kelly Steelman, where we're looking at education chatbots for digital newcomers. So what we're trying to do here is we are trying to build some AI assistants that are always available because they're AIs to help people answer technology questions. So this comes out of some work that they have been doing in the past, where they've been doing digital literacy tutoring for people who don't have strong digital literacy skills. And up to this point, it's been largely in-person tutoring. I believe they've done some experimentation with tutoring over Zoom. But the point is it's human involved. And as we know, humans have typical working hours. And even though they're probably always going to be better at assessing and tutoring somebody, there's reasons that it may be beneficial to also have AI assistants that can do a similar task. And this is challenging because we're trying to work with a population that doesn't have strong digital literacy and often doesn't know how to ask the questions in a way that will get them the answers they want. And so one of the things we've looked at with some of this early experimentation with like ChatGPT is that if you're not asking it a well-formed question, it will potentially misunderstand the question and answer a different question, which may increase the confusion of the person who's asking the questions. So what we're going to try to do to get around that is try to follow some of these methods that human tutors use, where they respond to questions in a way that helps probe out what the person's literacy is and also helps get them towards a better future where they can find their own answers as well. So building their skills in addition to answering their questions. So we want to do this by training these rhetorical strategies into a chatbot. That's a unique challenge on its own. I'm not going to go into that today. Another challenge here is that we're trying to develop some methods for identifying questions that indicate low digital literacy. That's something that we have started working on. Tagore is working on that with us, which is fantastic. I'd love to chat about that later if anyone wants to talk about that. And then once we can do that, we're also going to implement a retrieval augmented generation method to make sure that we are responding to these people asking us questions in a way that is factual. So that is a huge concern whenever we're using large language models is the response factual? So let's talk about retrieval augmented generation. Because this is really like the most popular method at this point for making sure that responses are factual. And we'll go over this figure in the right here, which I took from this blog post. It's a good figure. And we start off with a question. So let's say somebody wants to know who is the president of the US. So the first step is we take that question, we send it to an information retrieval service or something. And in this case, we're looking at Wikipedia. And we pull out from Wikipedia or whatever we're using as our database that Joe Biden is the 46th and current president of the United States. We take that information along with the query from the user, we feed them together into our language model, and the language model is able to look at this context provided by the information retrieval in addition to the query and give a factual answer. You can see how this could be potentially useful for situations where information changes. So maybe obviously in 20 years, we'll have a different president. And so this same model won't be stuck in the past if it was trained to know that Joe Biden was the president, if it's able to perform this information retrieval task on some database that's kept up to date. For our purposes, it lets us answer specific technology questions that we have in our databases. Yeah, so it's more efficient than incorporating new data. It's a really good method. So to use it for our work, we have a lot of historical data from past tutoring sessions, and that data typically looks like the following. So it has the types of questions that people had. It has the answers to those questions that the tutors came up with. And sometimes it has additional information like what types of rhetorical strategies worked, like how did I help talk this person through the solution, things like that. And so to use these resources in our model, obviously we're going to use retrieval augmented generation. That's the first step. The next step is we have to take all these resources and we have to split them into appropriately sized, topically similar pieces. So we want to be able to say, okay, if they're asking about how do I check my email from my phone, we need to find the parts that are only relevant to that. And if there was a bigger conversation where they asked a few questions, we want to focus only on the parts that matter. And then the last step is once we have these inputs split, we need to do some semantic indexing, which is a pretty straightforward problem. So we're going to talk about that. How do we split the data into appropriately sized, topically similar pieces? And the answer is text segmentation. So this was something I worked on during my PhD. Conveniently, it's a problem that we have to solve for this research project. And so I'm going to talk you through what text segmentation is about. So to get a good text segmentation, ideally, you want to take all the information for a given topic and create a boundary where that topic ends and the next topic begins. It's a pretty big research area. There's a lot of proposed solutions to the problem. But one thing that I thought was lacking was ways to evaluate text segmentation. So here's an example on the right. We have some text that's about the moon and Jupiter, and you can see that this is a pretty logical place to segment the text. So we go from talking about the moon to talking about Jupiter. And so, yeah, those are pretty clearly different topics. So the way that we generally segment text before my paper is that we take a list of all the chunks and we split them typically at the sentence boundaries, but not always. Sometimes we do it a little differently. And we indicate the chunks where the new segment starts. And that looks kind of like this. It's a set of ones and zeros where each index is a different sentence. Sometimes we represent that as a mass format. So this same segmentation we could represent as 3 sentences followed by a chunk of, or a segment of 2 sentences followed by a segment of 4, and so on. And these are the metrics that people have published before me. So PK was the first one. It's pretty common. People still use it because it's really simple and everyone has published it. Window diff was an improvement over PK. I'll talk about those in a minute. And then there's some boundary-based ones where they're trying to improve on these, but no one really publishes them at this point. But we can talk about them for a little bit. So what does this look like? Yeah, so I talked before about the boundary set versus mass format. So here's 2 different segmentations for the same data set. We can just look at it as masses, 1 sentence, 2 sentences, 2 sentences, or boundaries. And we often think about segmentation errors as a couple of different things. A near miss or transposition is where a boundary is off by like 1 or 2 sentences. A full miss is where we've just deleted a boundary or multiple boundaries. So maybe we think we should have a segment that starts and ends here, but we just don't get it. And those are the main errors that people seem to talk about. Sometimes you'll also see extra boundaries get inserted. So PK is the most common segmentation metric for text, as I was saying. And the way it works is you take a sliding window across your reference and your hypothesis segmentation set. And if they both have a boundary or they don't both have a boundary, it's good. You say that's correct. They have the same boundaries together. So you can see this full set of arrows here within this region, within this window. There's no boundaries. We're good. Within this set of regions, though, the hypothesis set has a boundary, but the reference doesn't. So that's bad. We're going to count that as an error. But then if we shift over one more with our window, we both have one boundary, so it's good. So that's how PK works. You count those up and you make an output based on that. I won't go into the math because it's not necessary for understanding this work, just conceptually. Window diff takes PK and it says, well, instead of just saying whether or not they both have a boundary, let's actually count the boundaries. And because we get weird behavior at the ends, let's put some padding on the beginning and the end. But basically, it's doing the same thing. We take the window across, we count the boundaries. Okay, they both have one segment here. That's great. They're great. Here, the hypothesis has one more segment than the reference. That's not good. So same kind of thing. Boundary edit distance is trying to count the number of edits that it would take to take your hypothesis and make it match the reference. And it's not as computationally as efficient, and it's not as easy to understand. And so people don't really use it, but it is an improvement, in my opinion. Yeah. But anyways, the problem with all of these different metrics is they all require you to have a reference set. So all of them require some human to go through your data first and say, this is where the boundary should be, this is where the boundary should be, etc. Or you have to have some segmentation algorithm that you trust go through the data first and say, this is where my segmentation should be. I think that having a computer that you trust or an algorithm you trust make the references set does not make sense, because if I trust a segmentation algorithm to do this, I'm not going to use a metric to assess how well, that algorithm did. That doesn't make sense to me. So in my opinion, if you want a good reference set, you need a human to do it. However, what I came up with in this paper is a segmentation metric that works without a reference set. And we published this last December at Experimental Methods in Natural Language Processing. And we called it a reference-free segmentation quality index, or SegRefree. Conceptually, really high level, we create this metric based on the content of the segments. So I'm making the implicit assumption that we want to do topical segmentation, and we want our segments to respect those topical boundaries. So I do this by using sentence level embeddings to represent each sentence, and that allows me to avoid having a human annotator. So because I'm looking at just the semantic sentence level embeddings, I don't need a reference set. And the way I use those embeddings is I treat segmentation as a clustering problem. So in clustering, typically we're looking to make sure that our cluster members are close together and that they are well separated from the next cluster. So this is a very similar problem, right? We want to make sure that we have a coherent set of topics within a segment. And then when we shift, it's going to be another set of topics in a different semantic space within our embedding space. And so I did this by taking an intrinsic clustering metric, the Davies-Bouldin index, and modifying it to work for sentence or text segmentation. To give you a very, very crude illustration of how this looks, let's say I have a transcript that's represented with these different shapes in our sentences. So we have these first two sentences we represent as red X's, blue O's, green stars. And each of those different color and marker combinations represents a segment. So in my embedding space, which I've projected into 2 dimensions here, I have a pretty good segmentation. So I have a nice tight cluster here for my red X's. It's well separated from my blue O's, which are here, and so on and so forth. And yeah, so keep going. Yeah, let's keep going. Sorry. To talk through how this is done, we start with sentence level embeddings, and I use for this work SentenceBERT. I looked at a few different ways of doing this, but SentenceBERT really performed the best. And that's based on BERT, which generates word level embeddings, and then it combines those to create a sentence level embedding. The original Davies-Bouldin index, which some of you are probably familiar with, is as follows. We start by taking the ratio of the cluster spread and dividing it by the distance between the centroids. So the cluster spread is the average distance between the cluster members and the centroid of a given cluster. And so we add that up for clusters I and J, and we divide that by the distance between the centroids of clusters I and J. So that gets us our ratio of cluster spread to cluster separation. Then we take a row-wise maximum. So we're only looking at the worst possible case for each I, and we average those. And that's the Davies-Bouldin index. It's pretty straightforward, but it doesn't really work for our task. And the first problem here is that because of the way that the semantic space works, the smaller the cluster is, the better it looks, because within the semantic space, sentences tend to move around constantly. Like you'll never get something that's in the exact same spot. And so you can artificially make your score better with the Davies-Bouldin index just by shrinking your clusters down until they're tiny, right? And so what I had to do to modify the Davies-Bouldin index to work for our task is I added this penalty term. So when I'm computing cluster spread, I divide by this factor of 1 minus the square root of the cluster membership, or 2, whichever is bigger. And that's what this penalty term looks like. And so it approaches 1 as the cluster size gets quite large and has less impact, but it tries to prevent clusters from being really small. The second issue with the Davies-Bouldin index is that it doesn't have good sensitivity in situations where a topic appears in multiple clusters. So to give you an example of what I mean by that, let's say my first topic I'm talking about is cookies. So I'm talking about which cookies I like, and then I'm going to talk about Davies-Bouldin clustering indices for a while, and then I decide I want to talk about cookies some more. Because those two topics of cookies are essentially the same topic, we're going to see very little distance between those two segments, right? And so if we're doing the normal Davies-Bouldin index, we're going to show that those two topics aren't well separated. However, that doesn't take into account the temporal nature of the conversation, where between those two cookie conversations, I talked to you about the Davies-Bouldin index. And so if we had segmented that Davies-Bouldin index out properly, those two actually would be really good text segmentations if they were, their own group, even though it's the same topic, because we have a topic in between them. And so the way that we incorporate this into the Davies-Bouldin index to make it work for text segmentation is we only compute the Davies-Bouldin index for adjacent clusters. So from one segment to the next, we look at the segment before and after it, assuming there's one before and after, which you won't have at the ends. And we only compute those cases. And so what that looks like mathematically, when we compute this ratio of cluster spread over cluster separation, we're only doing it for I minus 1 or I plus 1 from I for J. This is technically redundant because you end up with a sparse matrix, but it looks like this as well when you compute the row-wise max. All right, and so thinking back to our little 2D illustration, if we were going to compute this matrix of our ratio of spread over separation, we end up skipping the diagonal, obviously, and then we skip computing it for our cases between segment 1 and segment 3 because they're not adjacent. And then we perform the rest of the Davies-Bouldin index as before. So we take the max, we average those scores. And that's what this looks like in math. So I kind of walked you through this already, and I want to have time for questions, so I'm not going to dwell on this too long. So we did an ablation study to demonstrate why these two changes are necessary. And we had two main data sets that we worked with, which are pretty common text segmentation data sets. So the really famous one is the Choi data set. He's the person who published the PK metric, and so everybody tends to use this data set as a way to talk about text segmentation. And then we also use the Wiki 50 data set, which is a little more challenging, and it's taking Wikipedia articles and it's saying we assume that the Wikipedia article is segmented by topics in a way that makes sense. So we just take the Wikipedia articles, and every time there's a new heading, it's a new topic. Anyways, what we show is if we don't include the size penalty, we start to fail as we put extra boundaries in on the Wiki 50 task. If we don't include the adjacency requirement, as we delete boundaries, we are getting really bad correlations. So this is a table of correlation. Obviously, we want a correlation of 1 in the best case, but most importantly, it needs to be positive, right? And if we if we take the original Davies-Bouldin index, which doesn't have the adjacency requirement or the size penalty, we fail at, both the text segmentation boundary deletion and additional boundary addition tasks on these two data sets. We also looked at L1 distance and cosine distance. That didn't seem to make a huge difference between L1 and L2. Like I said, I'm talking way more than I expected to. So let's talk about how I validated this. So I took these two classic segmentation data sets and I came up with some experiments where I took the human golden reference segmentation and I made it worse progressively. And then I computed both a classic traditional segmentation metric and my metric, and I compared them and I showed that my metric behaved similarly to traditional metrics while making worse segmentations. And so because the behavior is similar, I'm saying, yes, my metric is probably good. So the first experiment I did was boundary removal. So all this is saying is I'm going to take a random boundary that's within my human reference set, and I'm just going to make it vanish. In this task, I demonstrated a really good correlation. So again, we're looking at correlation here between these 4 traditional segmentation metrics and my metric. And so PK, window diff, segmentation similarity, boundary similarity. On both these data sets, as I remove boundaries, we're seeing a good agreement between my metric and the existing metrics. Plotted, that's what this looks like. So this is the Choi data set on the left. This is the Wiki 50 data set on the right. My metric is the black square in both of these, which is on the left axis. On the right axis are all of the classic segmentation metrics. So super strong linear results here with Choi. With Wiki 50, it's a more challenging data set, as I said, but we still see a pretty good agreement between the two sets of metrics. I also did a segment splitting experiment. So what I do is I randomly take some segments and I split them in the middle. And again, I show a very strong correlation between existing metrics and my proposed metric. And what that looks like in plots is a little bit uglier, but there's still a pretty good agreement. The way that I've computed these, which I should mention, is I randomly did this 30 times where I took first one segment and split it, and then I randomly selected another one and split it, and then I averaged those. And on the horizontal axis here, you can see number of segments split. I did this experiment in a progressively degraded way where I kept, instead of just one segment, then it was 2, then it was 3, and so on, as a way to show how the behavior of these metrics change with additional segmentation errors. The last experiment I did with boundary transposition. So here I've taken a boundary randomly and I've shifted it over. And this is where things started to break down. With Wiki 50, PK and window diff start to have a negative correlation. And with the segmentation similarity and boundary similarity metrics, the correlation is low. This was kind of concerning to me, although I did find a paper here, which I've cited here, that says that existing metrics are pretty much awful for transposition. And so that made me feel a little bit better because now there's some uncertainty whether it's just my metric that doesn't work or theirs. So that was good to read. But yeah, this was a challenging experiment. You can see on Choi, we more or less have an okay agreement, but then on Wiki 50, once we get past one boundary transposition, my metric kind of drops back out and starts to say that maybe it looks better. So there are limitations to my method. But getting back to where we started, this will be helpful for our chatbot. So we have these long reference texts that are long narratives written by tutors. And we need to split them up so that we can put them into our models so that the model can reference the relevant parts. And the way we can use this specific work is it can provide a fair evaluation of the segmentation as we try different ways of segmenting these longer texts so that we can use them to help tutor people. So yeah, so that is what I had to talk about today.